Hello, welcome back. Stat 2050, University of Wyoming, online. Having a great time. So good. So good. Okay, so it's a new week. That means new stuff. But the nice thing about this week is that the process from last week carries over, and it's almost the same. Very, very similar to what we were doing last week. The math, conceptually, identical. And then the tool that we're going to be using is a little different. There's one other bit of information that we have to throw in, but otherwise it's just an extension of last week. But instead of proportions, right? That proportion, the idea there was like a gentle introduction into this idea. But we're going to be working with means instead. We're going to be making inference about the mean, right? Which is great. So you can kind of think of like last week as, challenge your friends at the bar kind of thing, like easy to do off the top of your head. Well, maybe some pen and paper and the internet. But that's very much easy to do when you're sort of, on your own, challenging, the norm in that kind of sense. But in this week, we're going to be doing very much what scientists do when they do bona fide research, right? So essentially, this stuff that we're going to be doing, I'll kind of write it over here just as a little intro. We're doing t-tests this week. Very similar to z-tests, but just like the z-test used the z-distribution, we've got a little bit of a different distribution we'll be using this time. Okay, but again, process super similar to last week. So if you got it last week, you're going to get it this week, I promise. But before we get into stats, I know, we got to do the album of the week, man. We got to do it. If you've heard of Phoebe Bridgers, that's great. If you haven't, you have to. Out of all of the albums I think I've suggested so far, which is now 5, I think that this one might be maybe not my favorite, but it certainly is different than all the other ones in a good kind of way. This is still kind of funky, still kind of I don't know, whatever. But this whole album reminds me of if you had let me actually backstep. You will like this album if you had an angsty teenager phase, and then eventually you broke out of the phase. If you're trying to get back into the phase, listen to this album. It's super good. It's super good. A ton of sad songs, but they're really well written too. They're not cliche sad. And some really fun kind of funky stuff. So here's what I would do. Here's what I did, and I found that this is the best way I think to listen to this album. First, listen to Motion Sickness. You've probably heard that song before, and then listen to Scott Street, and then listen to Funeral, and then listen to it from beginning to end. So you'll hear those songs a couple of times, but that's good Lord, that's a roller coaster. That's an emotional roller coaster, which is really great. So check it out. Check it out if you're looking to have, another angsty teenager phase. Okay, enough about that, I guess. Kind of a bummer. I hope you enjoy the album review or suggestions at the beginning of each week. I think it's really good. I think it's great. If you hate my music, then that's totally fine too. That's just a bummer for you. All right, so here we go. Into stats. Okay, so in this inference about the mean, and just kind of in general too, we usually have two situations. Okay, and there's a big asterisk right here with this too. The first situation is that we know what the population looks like, right? We know whether it looks like this, or the distribution, or whether it kind of looks like this, whatever. Where the only thing changing here, the mean is still the mean, right? Whatever. But we don't know the overall kind of spread of the thing, which is denoted by the sigma, right? Population standard deviation. In this instance, we might know what that looks like. However, this is so uncommon, right? We often do not know what the population really looks like. We might be able to find the mean, right? But the overall sort of spread of the thing, and by find the mean, let me take a step back. By finding the mean, estimating the mean. We might be able to get close. But as far as the overall kind of like distribution, the spread of this thing, we really, this is fairly uncommon. More often than not, we do not know what the population looks like. Okay. In fact, now don't tell anybody this. I'm pretty sure this situation, because there's a whole formulas and math and stuff that you can do, but I'm pretty sure that this has got big textbook written all over it. I think that this situation here exists so stat textbooks can print like 100 more pages. It just never really happens in real life, right? It happens in textbooks all the time, but in real life, often we really don't know, right? So don't buy into this. Don't buy into this. That's just big textbook trying to bring us down, This is more common, okay? So because of that, we have to use a different test, right? So in this case, we were using a z-test, right? Or we would use a z-test for the mean, right? Very similar process to what we were doing last week with we're just gonna, instead of the proportion, we're just gonna put in the mean instead, and it's a slightly different standard error formula. Again, who gives a rip? Because it never really happens. I'm sure you could find some situation where this does happen, but more often than not, we're working in this world, right? So we got to use a different test. And what's that test called? Woof! It's called a t-test. You've probably heard of it before. It's super commonly used, especially when you're comparing like two groups or one group against a known thing, whatever. And this is sort of a big family of tests developed by this dude. And this guy's name is William Seeley Gossett. He hailed from the United Kingdom in the late 1800s, right? And so you're probably wondering, what the heck does old Keaty have beer doing on the presentation? Well, that's a great question. Buckle up, because I've got a story for you. So, old Billy here was working at the Guinness Brewery as an experimental brewer, which is a pretty dope job title, I think. I think that'd be super cool. And so he was essentially, his whole thing was taking small samples from plots, right? Doing a little bit of magic on them, and then relating that back to the whole crop, right? The whole field or whatever. And this is all hops and barley and all that kind of stuff, okay? So he's taking these small samples, he's seeing whether or not, maybe adding fertilizer to one of them, right? And not to the other. How does that affect the overall growth? That's kind of what he was doing, right? So based on these small samples, he was able then to say, okay, probably the population, right, which this is the whole population, just the field of barley that they have, probably the population is going to be affected in some kind of way, right? Okay. So he kept doing that, and he kept developing this idea of taking these small samples and applying it back to the overall population. And then old Billy here was like, hey, Guinness, I think I've really come up with something very cool that would progress statistics into the modern age. Can I publish it? And Guinness was like, nope. Sorry, dude. And then he was like, hey, he came back a couple months later. He's like, hey, can I please publish this? And they're like, fine. But you can't use your real name, because we don't want people knowing that, this is what Guinness is doing. We just want, just the math, right? Just the math. We do not want Guinness, or don't want other beer people, brewers, to figure out, the genius of Guinness or whatever. When in reality, it's the genius of old William here. Okay, so William, Mr. Gossett, was like, all right, fine, whatever. So he published his findings, and he called it the long version, called it Students T-Test, because he published under the pseudonym Student, which is, I'm not really too sure why, but that's just what he chose, right? And so that threw statistics into the modern age at that point, right? Because at that point, stats was only like a kind of extra thing tacked on to math, right? And then didn't really have a lot of like real world application, so much, right? But then student over here, old Billy, was like, hey, let's kick it, and he did. And so anyway, why is it called a t-test? Well, he's over there in the United Kingdom. Everyone's first favorite drink is beer. Everyone's second favorite drink is tea, right? Now, I made that up. I made this up. The story about Mr. Seeley Gossett here is true. I'm not sure why it's called a t-test, though. So, do with that what you will. But anyway. He developed this whole thing, taking small samples and applying it back to the population when maybe it's not normal, right? Or maybe you don't know what the population standard deviation is, right? So he developed this idea of a t-distribution, okay? And let's read a little bit about it, and let's note some similarities here. The t-distribution is bell-shaped, right? It's also symmetric, and it's centered at 0 still, okay? Oops. But what's the deal? Well, it is more spread out. It is more spread out, and I will show you here in just a second, than the normal distribution. Because instead of using sigma, some value, right, for the known population standard deviation, it uses the sample standard deviation instead, okay? Now, samples can vary a lot, right? Because they're a function of sample size, right? So it turns out, let me erase all this too, that this whole thing, this is only one version of the t-distribution, right? This, is seemingly normal, whatever, seemingly normal. But it turns out that when you increase the sample size, it starts to change. Or if you decrease the sample size, it also starts to change, right? So for instance, a low sample size for this t-distribution would look kind of like this. Kind of gross. That's actually what it looks like, right? But then when you increase the sample size, it becomes more kind of normal, right? Sort of what we're used to seeing. Okay, so this is all tied up in this idea of sample size, but really, it's an idea of degrees of freedom. I don't know what that really means. Well, that's okay. We'll move on just for a second, and then I'll get back into this idea of degrees of freedom. But what I was saying earlier is that when the sample size increases, it turns out that t, when n increases, almost equals z. It is almost identical. And then when the sample size gets super large, right, super big, t is the same as the z distribution, which is crazy, right? So we kind of have this idea, I've got it down here too, where each one of these lines represents sort of a different sample size, right? So as this degrees of freedom goes up, that means the sample size is going up, right? So we can kind of see here that this yellow line that I'm drawing over in red right now, it's kind of fat, right? It's sort of like, it's got these wider shoulders, right? And it's not as tall as the normal distribution either, right? Because it's making up for that area, because we're using the sample standard deviation. It's making up for that area in the tails here, right? Kind of fat tails. But as that sample size increases, we kind of notice that it gets closer to the normal distribution, right? And so the black line, let's see if we can kind of see that. Yeah, the black line there is degrees of freedom equals 30. And then if we wanted to, sort of I'm not really the best at drawing, but eventually, when we get up to like 50 degrees of freedom, actually, I don't even think it's that high. I think it might even be closer to 30. Regardless, as that sample size, as this degrees of freedom increases, the z becomes just like the t becomes just like the z distribution, which is super special. Very cool that old Billy over there figured it all out, which is crazy. I think it's pretty crazy. Okay, degrees of freedom. What the hell? What is that? Well, it's a function of sample size. We kind of saw that with this idea of n. So n is the sample size minus 1. That's the degrees of freedom. But this is an odd-looking thing, right? N minus 1, that's like pretty easy. That's probably the easiest formula that we've had so far, N minus 1. What is that? Okay, well, technically, it's the number of independent pieces of information we have. Okay. What does that mean, though? Well, let me tell you a story. Let me give you a little example here. Using everyone's favorite gang, right? This is Seinfeld. So this is Jerry, Elaine, and George, and we have over here Newman. Arch rivals. They hate each other. It's kind of funny. If you've never seen the show, you should probably watch it. If you have seen the show, then you'll think that my analysis on these characters is spot on, I think. So let me just tell you this story, or let me give you this example. So we have Elaine here, we have Jerry, and we have George, and then Newman. I'm not even going to write Newman's name. George. Cool. And so they're at the diner, right, and they're saying, hey, we should probably split up the bill. Let's do it evenly so, everyone pays the same. No biggie, right? Everyone's cool with that. And it turns out that everyone just got new credit cards. They had just come out, right? So they're trying it out, And Elaine here says, why don't we just take the mean of our credit card numbers and we'll be able to pay for it, right? Well, that's not really how it works, but for this example, let's just assume that we'll entertain that idea, okay? And then Jerry is like, dope, I'm okay with that. Elaine says, George, what about you? George says, no. I know that Newman here has been looking to get our credit card information, right? And then Elaine says, hey, actually, dummy, it's not that big of a deal. And let me tell you why. So let's just say that the mean, we'll take the last 4 digits because I'm not going to write out this whole thing. Let's say the mean of the last 4 digits is 5262. I don't know, I just made something up. If this is your credit card, the last 4 digits of your credit card number, let me know. And let me know your address and your mother's maiden name. And then I'll be sure to change this in the future. Just kidding. Okay, so anyway, Elaine says, okay, George, listen. If this is the mean, then that means we had to calculate it using 3 numbers and then dividing it by the number of people that we have, right? And so if we keep at least all of our numbers secret, right, there's no way that Newman over here will be able to figure out any of this information, right? With this one piece of information, right, this is only one piece of information, all of these other things are related, are kind of dependent on this bit of information. No, other way around, sorry. This bit of information is dependent on all these other things, right? But if you don't know it, then it's fine, right? If you don't know these 3 things, then we are good, okay? And we know that all of these credit cards existed before we did any math, right? It's not like once we calculated the mean, then these 3 credit card numbers came into existence, right? That did not happen. They're all independent of each other, okay? And then Elaine goes on to say, and actually it turns out that if I were to give my last 4 digits, you still would not be able to figure out any of the other 2, right? So you're safe, right? So even if Newman figured out mine, he would not be able to figure out George's or Jerry's, right? However, then Elaine says, but we have to be careful because if 2 of us accidentally give out our numbers, then yes, we will be able to figure out, or at least Newman here, will be able to essentially solve for X, right? And figure out the last bit, right? So what we're saying here is that the number, including the mean, right? Including the mean, the number of independent pieces of information we have are here, here, and here. But once we have these 3 pieces of information all tied together, this last credit card number is easily solvable and totally dependent on everything else here, right? Okay, so for Newman to figure out a credit card number, any credit card number, he needs n minus 1 bits of information, where n represents 1, 2, 3, 4 pieces of the information, right? right? So with this 1, 2, 3, right, he only needs 3 pieces of information to find the 4th, right? And so that's kind of what we're doing with this idea of degrees of freedom, okay? Where if you have the mean, you can have all of your data, right? Let's say that you had 10 pieces of data lined up, and the mean, you had its mean, 10 pieces of independent information, and the mean. You would be able to figure out, or let's say that 9 of those pieces of information, 9 of those data points, are independent, right? And the last one, when you have the mean, is dependent on all the other ones, right? So you have n minus 1 pieces of independent information, n minus 1 degrees of freedom. That's kind of the idea there. Okay, so where does that come into play? Well, actually, yeah, I'll draw it out since I have this. Degrees of freedom was that function of sample size, right? So let's just say we have a t-distribution. Kind of saw this in the last picture too. But degrees of freedom equals 1. Okay, so how do we find that? Well, if we kind of work this around, we know that degrees of freedom equals n minus 1. That means that we have 2 things in our sample, right? Okay, kind of a roundabout way to do some very basic algebra there. But with this degrees of freedom equals 1, that means the sample size is really low. And so since we're essentially trying to estimate, oh my god, what is that? What is that? Don't know. Okay, sorry. So since we're trying to estimate the population standard deviation with S, right, with the sample standard deviation, with only a sample size of 2, which is what we have in this case, our guess of what the population looks like is going to be really bad. It's going to be so bad. But we know that as we add in more information, right, as we add in more information, we can get kind of closer to what the actual population might look like, right? So this would be degrees of freedom equals 5. That means that we have a sample size of 6. Still kind of small, but we're getting closer, right? We're getting closer. And then let's say, again, that we maybe have 15. So sample size, actually, let me make it so it's more rounded. So degrees of freedom equals 14. That means we have 15 in our sample, right? That might look more like a normal distribution. And then when we get up to, theoretically, we can even plug in infinity, which is wild. But that turns out to be totally normal, gracefully drawn by yours truly, right? Where we have a mean of 0 and a standard deviation of 1, right? So this would be where 68% of the data are, right? And then go further out that empirical rule, right? So the deal, ouch, I just hit my knee on my table. The deal here is that as, let me do it in this color too. As n increases, which also means degrees of freedom are increasing, we're actually going to use mathematical kind of arrows here. T approaches z, okay? And then, like, if n equals infinity, which means degrees of freedom is also close up there to infinity. I'm not even going to write it. T equals z, right? So that's the whole idea. That is the whole idea here, right? As the sample size increases, our t distribution becomes very similar to the z distribution, right? Which is good for us. All right, going into the basics here. So a t-test just tells you how significantly the differences are, okay, between groups or between your mean and some known other value, right? But oh my lord, we gotta make sure we get this. We have to make sure we get this, because this is where people get really tripped up in real life, right? They took stats when they were like 14 and then never thought of it after that, right? So when you see this word in English and when you see it in stats, 2 totally different meanings, which I hate. That's just the convention, right? That's just the words that we use. So in English, significant means that it's just like a big deal, right? We can actually just say that it's like notable. I think that's how you spell notable. So it's just something that you see that is noteworthy, right? But in statistics, when we say significant, we actually mean that what we saw was unlikely due to chance, right? Okay, so whatever we saw, it is totally up to either chance or not, right? It's actually some function of something, right? But if it's statistically significant, then that means that the result is unlikely due to chance. Now, can you have something that is statistically significant but not practically significant? Yes, big time. And then can you have the opposite? Yes, you can, right? These two, I guess, adverbs here, or maybe adjectives, depending on how you structure it in your sentence, are totally different, right? Okay, so we will use the word statistically significant all the time, but do know that it's not necessarily the same as notably significant. Okay, and we know that when we're doing all these tests from last week, especially, you get these p-values, and that's just the probability, right? That's the probability that your result occurred by chance, right? All tying back to this idea of statistical significance rather than the idea of practical significance. Okay. I'm going to pause it here. Actually, no. Let me do this one thing. Sorry. So, t-tests, right? Still in the basics here. We got 3 different types, right? 3 different types. This one is the easiest to do. This one, number 2 here, has got a little bit more work, and then the paired t-test is the strongest. I've kind of done this in order, so weakest to strongest. And we can kind of see, right? We'll go into more detail here in a second, and here in the coming days and coming lectures, we'll say. But in this next video, I'm going to show you how to do a one sample t-test and sort of what they are, right? We're doing this idea of testing a mean, right, against something else, some other known value, right? Some other known sort of hypothesized value. Very similar to our proportion tests, where we say, the known proportion is 80%, but you went out and calculated that it might actually be 70%, right? Same deal, but we're doing means instead. So I will see you there in just a second.